I'm afraid we have to talk again a little bit about the times. So that's the present status. But one of you just told me, and I think it was the one who objected against doing it Friday from 2 to 4. He told me that now he would be available Friday from 2 to 4. And I wonder if it would be a good idea to move this 2 hours to the front. So should we do this? Should we say Friday 2 to 4? Or is there anyone who would not like to do this? So maybe it's a good idea so that you could go home earlier. So then, of course, I have to look for a room. But as far as I remember, Friday afternoon was not too bad. So there should be a chance that we find a room here in this building. And then the second thing we should decide is which of these slots we use for the tutorials. Actually, I have a strong preference to do the tutorials here. And the reason is the following. On Wednesdays, our Graduiertenkolleg will arrange colloquia. This will take 4 times during the term. This means on 4 Wednesdays. First, the PhD students will not be here. And I guess also I'm expected to be at this colloquia. So, of course, it's very inconvenient to shift 4 lectures. It would be much easier to ask a colleague to do the tutorial instead for me, or maybe just to give the sample solution to one of you, and so that you can do the tutorials among yourselves. I think this should also work. So I think it's not absolutely necessary that I'm here during the tutorials. But of course, I have to be here during the lectures. So that's the reason why I think it's a good idea to do the tutorials here. If there's not a strong objection, then we would have lectures here and lectures here. Yeah, is that okay? Yeah. Good. So then hopefully that's now the final schedule. Then I've seen that my first lecture, the Wednesday lecture, is now available. The video recording is now available. I've seen that, well, it is readable, what I've written on the board, but I think it would be easier readable if I write a little bit bigger. So I will try doing this in the future. So hopefully it will then be better readable. But it is readable, and that's also understandable. So I think the quality is not too bad. Today I will send around the first chunk of the lecture notes. So I told you that I type everything up and send it by email to you. I think that's the easiest way because not everybody has access to Stud IP. So I will send it around by email to everyone who has signed up. So if you have not yet, you have not, then you should do it. Please readable so that I... Okay, and I will also send around the first worksheet today. So then you have until Wednesday to have a look at it. Well, actually, the first worksheet will be very simple. It will just be about space-time diagrams where you have to think a little bit how to do some drawings. So I think you wouldn't need much time for preparing this first worksheet. So we could discuss this next Wednesday. Yeah, we discuss this together. And I said my hope is that one of you comes to the front. Of course, if this is more comfortable for you, you could speak German, of course. I think we can... Those of you who do not understand German, they will see the formulas and maybe get along with this anyway. Or we can translate a bit. So if you don't feel comfortable with English, of course, you can speak German during the tutorials. But on the other hand, it might be a good exercise for you just to practice your English. As a physicist, there's a good chance that in your later life you will be in situations not from time to time where you have to speak English. So it might be a good opportunity just to practice your English a little bit. Okay, so much for the organizational things. And then we can continue. I was just presenting a sort of timeline where I try to give you an overview how the historical development of relativity proceeded. And I think the last thing we had on the board was Fritz Zwicky's search for the gravitational lens effect. Any questions? No, okay. And the next thing I have on my sheet here is the year 1939. Robert Oppenheimer. I think everybody knows his name. This was a person who was a scientific head of the Manhattan Project. He has a building of the atomic bomb. He was a theoretical physicist, and he did quite a lot of very fundamental things in theoretical physics, and he wrote a few papers also about general relativity. It was not his main subject. He was mainly working on quantum theory. But this is one paper by him with a student, whose name was Snyder, and they did a very interesting calculation. They calculated how a ball of dust would collapse under the influence of its own gravity, according to general relativity. And what they found was that the whole thing would collapse in a finite time into a singularity. Yeah, so they calculated the gravitational collapse of a ball of dust. Ball means spherically symmetric. Yeah? And dust means there's no pressure. So they are just gravitating particles in this ball, but they don't exert any pressure onto each other. And actually, under this assumption, one would say, well, it's not too surprising that this would collapse to a singularity. There's no pressure that could prevent the collapse. And because there's perfect spherical symmetry, what else should the particle do than just move on radial lines? So they have to come together at the center at one time, right? So actually, it doesn't look too surprising. But we will come to that later. We will see that this property of forming a singularity actually is not just a consequence of the high symmetry and of the idealization, but that the equations of general relativity have a strong tendency to form singularities also under more general assumptions. That was the work with which Roger Penrose and Stephen Hawking became famous. So this was the first calculation of a collapse, and in a sense it was a predecessor of this famous work from the 1960s by Penrose and Hawking, to which I will come in a few minutes. In 1956 then, something happened which I had already mentioned when we talked about books on relativity. I mentioned Wolfgang Rindler, who was one of my teachers, and he wrote in 56 his PhD thesis. And in this PhD thesis, he introduced the notion of a horizon, of a particle horizon, of an event horizon. And these notions turned out to be extremely important and extremely useful for the understanding of many things in general relativity and particle horizons. And actually he did this originally in cosmology. So he looked at cosmological solutions and introduced these notions in this context, but later they became, people realized that the same notions are also very useful for other things. Only a few years later, people realized that this notion was very useful in order to understand this famous Schwarzschild singularity. We had briefly talked about the Schwarzschild solution, which describes a spherically symmetric object, the gravitational field outside of a spherically symmetric object, I should say. And I already mentioned that there is this strange singularity at a particular radius value, which is called the Schwarzschild radius, which is usually hidden inside the body for ordinary stars. But one could think of what happens if the stars compress so strongly that it is outside of the body. And it would have a singularity. You would have zeros in the denominator. And nobody understood this for many, many years. And the first people who understood this actually, I think, although they don't mention it explicitly, I think they were guided by these ideas of Rindler. They found the explanation. And actually, a couple of people did this simultaneously. One of them was David Finkelstein. Another one was Martin Kruskal. And then there were a few others, which were certainly later than the others. Actually, there's a priority quarrel between these two things. The publication by Finkelstein is earlier, but as a preprint, the work by Kruskal was circulated already before Finkelstein published this paper. So one could debate about who deserves the priority for this. So anyway, what they did, they explained the singularity in the Schwarzschild solution. at this value which we call the Schwarzschild radius r equal rs as a horizon. This means it is not a singularity in the sense that something bad happens if you are at this point. You won't feel something particular if you are at this point. What happens is that if you once has crossed this sphere, this surface, this spherical surface, then you can never come back. Yeah, it's a horizon in the sense that you can cross it only in one direction. You can move from the outside to the inside, but then not back from the inside to the outside. So if you are stupid enough to cross this horizon once in your life, from the outside to the inside, you will never come back to the outer world. That's what we mean by a horizon, as a horizon. So you cannot, or you, I've written you, maybe I should write this more precisely, no signal. In particular, a massive body, like each of us is, a massive body is a signal, right? This is a massive body, I can use this as a signal, I just throw it, and if it hits your head, you will realize, aha, this person wants to tell me something. So any massive body is a signal, so the word signal is more general. No signal can escape from the region r smaller than rs to r bigger than rs. That's something we will discuss in great detail when we talk about the Schwarzschild solution. And this property, that there is a surface formed which, or an area formed from which no signal can escape, this was called a black hole, a word, of course, everybody knows, but which is actually a fairly recent word. It was coined by John Wheeler only in 1967. So this word did not exist at the time when Finkelstein and Kruskal actually found what was going on. Finkelstein called it a one-way membrane, if I remember correctly, expressing the fact that you can go from one side to the other, but not from the other back. So this was a very important step in the understanding of general relativity. You see, Einstein died in 1955. So he didn't live long enough to see this happen. So he never understood what happened at r equal rs. He had ideas which were completely wrong. Whatever he wrote about r equal rs was completely wrong. Okay, so this was important thing on the theoretical side. At about the same time, there was also important progress on the experimental side. Maybe I should use. You remember we have talked about 3 predictions for experiments of general relativity, which were found by Einstein immediately after he had finished the theory. The first, in chronological order, the first one was the gravitational redshift, which was just a consequence of the equivalence principle, and that was at this time not experimentally verified. The second one was a perihelion expression, a perihelion precession of Mercury. This was known already. So it was an explanation of a known effect. And the third one was a light deflection at the sun, which was not known at the time when Einstein predicted it, but verified very recently, 4 years after the field equation was around. So the one what was still open was a gravitational redshift. This was not verified for several decades. It was only done in 1959. And it was done by Pound and Repka. What are the first names? R and G. R. Pound and G. Repka with B or P? B. And they did it in a surprisingly simple way. They did it in an ordinary building of a height of 22 meters. So they just sent a light signal from the bottom of the building to the top of the building, and it arrived with a certain redshift near the top. And this was a very small redshift, but at that time, the Mössbauer effect already existed. The Mössbauer effect allows to measure frequencies with very, very high precision. This was just invented at about the same time, a few months earlier. So they used the Mössbauer effect in order to measure the frequency with very high precision. And this allowed them to verify this general relativistic effect. So they measured the gravitational redshift in a building of just 22.5 meter height. And they verified the relativistic values, to within about 10%. Verified prediction. By general relativity. To within 10%. So now all three so-called classical tests were experimentally verified. So this was on the experimental side. The next step is again on the theoretical side, 1963. Then came the next important step about solutions which describe stars. Up to that time, not much more than the Schwarzschild solution was actually known. There were a few other things for an infinite cylinder and things like that, which are a little bit over-idealized. But models which could really describe a star were not known, or some other astrophysical object at that time were not known, other than the Schwarzschild solution. And the next step in this direction was made by this gentleman, Roy Kerr, mathematician from New Zealand, and he found a new solution, which is then called the Kerr solution, obviously. Found a new solution of Einstein's field equation. I should write Einstein's vacuum field equation. So it describes only the outside of some object. Vacuum field equation. And people fairly soon realized that this describes a rotating black hole. Yeah, so it's a rotating variant of the Schwarzschild spacetime. Schwarzschild is spherically symmetric, so it describes an object which does not rotate, because a rotation axis obviously would violate the rotational symmetry, right? But this applies to an object which has a spin, which rotates. And it must be a black hole, actually. Found a solution that describes a rotating black hole. And when people look for black holes in the universe, so you have probably heard that there's fairly good evidence for the existence of a very massive black hole at the center of our galaxy. When they look for such an object, they use for the theoretical description the Kerr matrix, the Kerr solution. So they think that the Kerr solution is a good mathematical model for describing these black holes at the center of galaxies. So that's a very important new solution of Einstein's field equation. And if there is time enough, maybe in the last part of the semester, I will tell a little bit about the Kerr solution. It's much, much more complicated than the Schwarzschild solution. So the mathematics is fairly involved, but maybe I can talk a little bit about some basic properties. Then come back to cosmology again. 1965, there was a very famous discovery, which earned the people who did it the Nobel Prize. These were Arno Penzias, German-born radiophysicist, and Wilson, R. Wilson. They discovered the cosmic background radiation. And this won them the Nobel Prize. When? 78. Some people find it, kind of a scandal that only Penzias and Wilson got the Nobel Prize. There was a third person involved by the name of Robert Dicke, who predicted the cosmic background radiation, who explained to these two people what they had discovered, They themselves didn't realize it. They had weird ideas of where this funny signal could come from. So Dicke explained it to them, and he had a theory to explain in which way this cosmic background radiation is produced. He was still alive in '78, and many people think it's a scandal that Dicke didn't get the Nobel Prize. In my view, he had deserved it more than these two, because they were lucky. Yeah, they found it, but they were just lucky. They didn't do much in order to earn it. But anyway, sometimes you get the Nobel Prize just for good luck. Actually, I once heard an interview by Penzias himself where he said, very quite openly and quite frankly said, yeah, it was just good luck. Yeah. He didn't say, I did a very, very, very great scientific work in order to earn the Nobel Prize. So he's quite honest about this. Okay, so this was the Nobel Prize for the cosmic background radiation, which of course is until now the strongest support for the Big Bang hypothesis. Yeah, because we think we see the remnants of the Big Bang in terms of this background radiation. Some people try to explain it in a different way, but the standard explanation is that this is a remnant of the Big Bang. Also, in view of gravitational waves, there was something going on the experimental side in 1965. Joe Weber started his long time search for gravitational waves. And what he used is called a resonant bar detector with resonant bar detectors. So basically, this is just a cylinder, maybe that size, maybe even a little bit bigger, something like that, certain diameter, certain length. And the idea is that this thing will start oscillate. And if you choose the size appropriately, then you will have a resonance effect so that it oscillates in a measurable way if a gravitational wave comes through. So that's the basic idea of these resonant bar detectors. A few of them are still used, but nowadays they have been mainly replaced by other sorts of detectors, the so-called interferometric detectors. So people hope nowadays that they will find very soon gravitational waves with the help of interferometric detectors. So these objects are a little bit outdated. So actually they were, in particular Weber, worked with these things for many, many years. Once he even claimed that he had found a gravitational wave, but nobody could reproduce this signal. And if you have just one signal, which nobody else had seen, then you cannot do anything with this. So, well, the general impression is that until now, nobody has actually detected a gravitational wave, and that Weber just measured something else, which he erroneously thought to be a gravitational wave. On the theoretical side, we had then, in this period from 65 to 70, this development which I find very, very intriguing and with which I dealt for some time, which I studied in fairly great detail. This is the so-called singularity theorems of Penrose and Hawking. I think most of you will have heard about this. I think the names are known to everybody, right? Roger Penrose, famous mathematician, now also a fairly old gentleman, I think around 80. And Stephen Hawking, of course, I'm sure everybody knows. He turned 70 just recently, a few weeks ago, or a few months ago. They proved their famous singularity theorems. And very roughly speaking, what these theorems say is the following. They say that under very general assumptions, not under strong symmetry assumptions or highly idealized matter models, under very general assumptions, fairly general assumptions, Einstein's equations have a tendency to form singularities. So if you calculate a collapse, not under these highly idealized conditions which Oppenheimer and Snyder had considered, but under more realistic conditions, with a realistic matter model, not perfectly spherically symmetric, nonetheless it will end up in a singularity. What enters into these theorems are assumptions only of the sort that the energy density should not be negative, Everybody would agree that this is a reasonable assumption. And yeah, some other, maybe more technical, not technical, but nonetheless fairly general assumptions. Yes, some of them are even generic in the sense that they are satisfied in almost any space-time, yeah, under almost arbitrary conditions. So under very general conditions, Einstein's theory produces singularities. And of course, that's the problem to understand these singularities. And the explanation which most people would accept is that this is just an artifact of the classical theory. If we once have a quantum version of general relativity, then these singularities would go away. But nobody was able to work this out until now. So it's just a hope that maybe sometimes in the future we have a quantum theory of general relativity, and then this problem will go away. At the moment, it still exists. So the theory produces singularities. And if you think about applications, this could be the collapse of a star. It could also be the singularity of the whole universe. Yeah, if you make a model of the whole universe, again, under fairly general assumptions, you will have something like a singularity. You will have a Big Bang model or a Big Crunch model. Yeah? So models which do not have these singularities are difficult to produce within general relativity. And in particular, this collapse of stars and what actually happens if such a star has collapsed and if a singularity has formed, this is an open question. And I think nobody really understands what's going on there. So that's one of the open problems in connection with general relativity to understand this. But that's too technical, so I will not be able to talk about this here in this course. It could be a good subject for a follow-up course. So maybe in the Graduiertenkolleg we could have a special lecture about this sometimes in the future. Actually, I've given already 2 times courses on singularities theorems. So I talked for the whole course only about these theorems. So you can spend a lot of time with them. Okay, then let's come back to experiments. 1971, there was a very funny experiment, actually. It made really people were really laughing when they read this because it was so surprisingly simple, and it's really a joke that nobody else had come to this idea before. The people who did it were Häfele and Keating. And Keating, they verified relativistic clock effects, and that's not just the standard twin paradox, which you know from special relativity, but also general relativistic clock effects, that the clock ticks in a different way if it is low in a gravitational field in comparison to when it is up in a gravitational field. Also, this gravitational clock effect, this relativistic clock effect, was verified by them in a very simple way. They just took atomic clocks on a commercial airliner, flew around the Earth, and compared the clocks with other clocks which were standing on the Earth during the whole time. And the accuracy was great enough so that they could verify these effects. It was a paper in Nature, and everybody was extremely surprised that this actually worked. So they verified relativistic clock effects. It was the first really macroscopic, quite explicit verification of the ordinary special relativistic clock effect, which we call the twin paradox, although there's nothing paradoxical about this, and also, as I said, some general relativistic effects. So they verified, I just use the plural form, relativistic clock effects, without specifying this, by taking atomic clocks around the Earth on commercial airliners. There are pictures where you see them in their seats in the airplane with these atomic clocks in the seats next to them and smiling into the camera. Commercial airliners. So it's taking atomic clocks around the Earth on commercial airliners. And they measure time differences with respect to stationary clocks, clocks which were not moved around the Earth but stayed in the same place during the whole time. Yeah, I think of a few nanoseconds. Yeah, that's what I wrote here. And that was enough to verify these relativistic effects. The effect that the clocks were sometimes high in the air during the flight, so higher up in the gravitational field than the other clocks which remained on the Earth. It makes a very well measurable effect. Yeah? So it's not just the ordinary twin paradox, it's also this gravitational effect, which was very well measurable. Okay, this was a funny thing. I really think this was a good joke. Okay, I hope that's readable. Next item on my list is again about Stephen Hawking. He was famous for two things. The first was in the 60s, the singularity theorems, which he did in fairly young years. So he actually began thinking about this before he had his PhD. And then as a very well-established scientist in the 70s, as actually a already fairly famous scientist, he did another very important thing. He put forward what we now call Hawking radiation. He found or I should say he calculated, it's really a mathematical calculation, calculated that black holes should emit radiation, and this sort of radiation is usually named after him, so we call it Hawking radiation. By that they lose energy, so of course the only material which they have in order to produce energy is their mass, so they would lose mass, and if this process holds on for long enough time, then they would actually vanish, so they could evaporate by emitting radiation. Actually, this happens fairly quickly for small black holes. For the thick black holes, like the one at the center of our galaxy, you can completely forget about this. Yeah, it would take longer than the universe will ever exist. So this evaporation of black holes is relevant only for fairly small black holes, if they exist. They are a matter of speculation. And he found this, he calculated this, not on the basis of classical general relativity. On the basis of classical general relativity, black holes would be stable. He used a sort of combination with quantum ideas, but not in the sense that he quantized the gravitational field itself. Such a theory doesn't exist. So there's no existing theory of quantum gravity, but he quantized the matter on the background of the gravitational field. So he did what we call quantum field theory on a classical background. Yeah, in the realm of this theory, this was calculated. in the theory, in quantum field theory, I should write, in quantum field theory. On a classical spacetime. So the spacetime itself, the gravitational field, the spacetime geometry is not quantized. Hawking radiation has not been observed until now. It's a purely theoretical concept, but well, there's fairly good theoretical evidence that it actually exists. Also in 1974, a person won a PhD, won a Nobel Prize for it, or did the work, which later he earned him the Nobel Prize with his PhD thesis. That's very rarely that you get a Nobel Prize for a PhD thesis. And the person who achieved this was Russell Hulse. And the thesis advisor was Joe Taylor. And what they did was they observed a binary pulsar, which is a partner in a binary system. So it goes around another star. Yeah? Two stars which rotate around each other, and one of them is a pulsar. So it emits radio pulses in a rhythmical way. And what they observed was that this pulsar loses energy. And they explained it by saying that this energy was radiated away in terms of gravitational waves. So this observation is usually recognized as the first indirect evidence for the existence of gravitational waves. There were no gravitational waves observed directly, in the sense that you have a detector and it makes click and tells you, aha, now a gravitational wave has gone through the detector. In this sense, it has not been detected until now. But in an indirect sense, that we see objects in the sky which lose energy, and the only way in which we can explain this is that they lose this energy by radiating it away in terms of gravitational waves. This is based on the work of Hulse and Taylor. So they found they were radio astronomers, so they made the relevant observations. And actually, these radio observations were the subject of the PhD thesis of Russell Hulse. So they found that the binary pulsar, yeah, he has a funny name. It's just related to his coordinates in the sky. PSR stands for pulsar, and then comes 1913. That's the right ascension. He has this coordinate in the sky, 19 hours, 13 minutes, and plus 16 is the declination, 16 degrees from the equator upwards. Found that the binary pulsar loses energy. To be interpreted, it's generally accepted. Of course, you cannot strictly prove that it must be this way, but there's very good evidence to assume that this energy is radiated away in terms of gravitational waves as being emitted in terms of gravitational waves. And as I said, this earns them the Nobel Prize. When? 93. In the meantime, there are many other, quite a few other binary pulsars. There's also one which is really a binary pulsar in the sense that both partners are pulsars. Then, of course, you can make much more accurate observations. So there are several objects of this sort now which are studied in great detail and which actually provide the best tests of general relativity we have until now. So you can test the equations of general relativity to a much higher accuracy than in the solar system with the help of these binary pulsars. We have radio astronomers here in Germany who are doing this in Bonn. That's Professor Kramer and his group. So they are the leading experts in this field. Okay, I have 4 or 5 more items on my list. The next one is gravity probe A. which was a satellite project of was a primitive sort. It was a rocket. They put a hydrogen maser onto this rocket, shot it upwards, and let it crash down again. That was the whole experiment. Took about 2 hours or so. And what they measured during the experiment was the gravitational redshift. So of course the rocket could go much higher than 22 meters, as it was in the Pound-Repka experiment, so they could verify this effect to a much higher accuracy. So they measured the gravitational redshift. Gravitational redshift with a hydrogen maser. A maser, as you certainly know, is the same as a laser, just with microwaves instead of light. Hydrogen maser with a hydrogen maser on a rocket. So the height was, the maximal height the rocket reached was something like 10,000. Is that true? Let me check. 10,000 kilometers, yes. And the accuracy with which the relativistic result was verified was much higher than in the Pound-Repka experiment. Pound-Repka had 10% and they had 10 to the minus 5. So that's much better, of course. So the gravitational redshift is now measured with a quite good accuracy. Actually, nowadays much better than this. But already in '76, this was a very good verification. I had mentioned already the gravitational lens effect, the bending of light, which could hypothetically be so strong that multiple images are formed. I told you that Fritz Zwicky looked for these objects. He died in the early '70s, so he didn't live long enough to get to see the first multiple image actually detected. It was in 1979. It was done by Dennis Walsh and his collaborators. Found the first double image produced by the gravitational lens effect. So you see two images of an object. The object is actually a quasar. So you see two images of a quasar in the sky, and there's very good evidence that there's only one quasar in nature, and you see two images of this thing. And they come about by the gravitational effect on the light rays from an intervening galaxy. So the galaxy bends the light in such a way that there's one image related to this path and another image related to this path, and so you see two images in the sky. So the first candidate was found in '79. And this is, well, if you speak of the twin quasar, then you mean this object. There are other twin quasars, but if you say just the twin quasar, you mean this one. And again, it is characterized by its coordinates in the sky. Q stands for quasar, and the coordinates are 9 hours, 57 minutes, plus 65.1 degrees declination. So if you take a map of the sky and look these coordinates up, you will see that it is in the Ursa Major, what we call in German großer Wagen, or in English the Big Dipper, yeah, großer Löffel. That's how they say in English. So that's here on the northern sky, but unfortunately the object is so weak that you cannot see it with a small telescope. You need a really big telescope. It's something like 16th magnitude or so. Okay, so this was the first of these multiple quasars. There are quite a lot of them now known, and the gravitational lens effect is now by the gravitational lens effect. I forgot this here, sorry. So this is now an important tool for astronomers, actually one of the most important tools to find matter which is not visible because it doesn't emit light. It was just observable by its gravitational field. So for this you use this gravitational lens effect. So more or less all the information, or most part of the information we get about dark matter comes from its gravitational effect. 94. The GPS is going into operation. Here's a, what is it standing for? Global positioning system. Yeah, what many of you use in the car for navigating. GPS is going into operation. And now you may ask me, why do you say this in a lecture on general relativity? What has it to do with general relativity? Well, actually, it wouldn't work without general relativity. So this system consists of satellites, something like 30 satellites which are in the sky. And your navigating apparatus receives signal from these satellites. And it receives signals with a very high precision as far as the time resolution is concerned. So what is the most relevant thing is the travel time of the light from the satellite to your position. And the effect of the gravitational field on this travel time is so big that you have to take it into account. Your navigating system would lead you in a completely wrong direction if general relativity wouldn't be taken into account. Both special and general relativity is really needed for this. And we usually say this, 1994, this was a time when general relativity entered our everyday life. Yeah, so we really need it now in our everyday life. Up to that time, it was a fairly theoretical thing, which has nothing to do with our practical life. But for the GPS, which for many of us is an object of everyday life, it really is needed. So that's the reason why I mention it here. It's already. I should hurry up a bit. But I have only 3 or 4 more issues. No, this doesn't work. Oops. Okay, 98. What is it called? Supernova cosmology? Yes, supernova cosmology project. Supernova cosmology project. Found evidence with the help of a certain type of supernovae. So that's why it's called the Supernova Cosmology Project. Found evidence, actually very good evidence, for an accelerated, and that's the word on which the emphasis is, for an accelerated expansion of the universe. So up to that time, most people thought, okay, the universe is expanding. There's fairly good evidence for this since many years. But most people thought that the expansion would become slower under the influence of gravity, which pulls the galaxies back, right? So the idea was there was a big bang, it flew apart with a very high initial velocity, and then the expanding velocity becomes smaller and smaller in the course of time. That was the ordinary assumption. But they found evidence for the fact that it's not that way. The expansion becomes stronger. Yeah? It's accelerating, expanding. And you need a reason for this. Einstein's equations, if you use them in the ordinary way, as they had been used until this time, didn't allow this. You needed an extra ingredient. You needed a certain amount of matter, a matter source. You have to invent a certain matter source which produces this expansion. And that's what we call dark energy. Yeah, so you have to feed into Einstein's field equation an additional component of matter, a hypothetical component of matter. Then you can explain the thing very nicely. But if you don't do this, then it doesn't work. So this requires introduction not only of dark matter. I told you this was around already since many decades. Introduction of not only dark matter, but also dark energy. Now the question is, what's the difference? Not only the fact is that the dark matter is clumpy. Yeah, it's concentrated in the galaxy clusters. So that's what we call dark matter. But also of non-clumpy, so I write homogeneous. So equally distributed over the universe. That's what we call dark energy. No, the quotation marks are in the wrong side, on the wrong place. It should come now, dark energy. So that's something you need in order to explain this acceleration. If you accept it, then it's fine. But of course, you should come up with a real theory what this dark energy is and where it comes from and how it can be explained. So that's still an open problem. So you postulate it, then you can explain the observations, but of course you would like to know what it really is. And that's an open question until now. Nonetheless, the pure fact that the universe is accelerating was considered by the community so important that it gained the people who did this a Nobel Prize. You certainly remember, this was just recently, last year. So the three leading scientists who were involved with this, by the name of Perlmutter, Schmidt, and Ries, they won the Nobel Prize for this last year. Penultimate thing on my list is next progress in the gravitational wave measurements. In 2002, where the first science runs, so the first real measurements of 2 gravitational wave detectors, or actually 3, because one project involves 2 detectors. So of the gravitational wave detectors, which we know by their acronyms. One is called LIGO, that's the American version. Don't ask me what LIGO stands for. So it's an abbreviation of something, USA. And the other one is GEO 600. I can tell you what the 600 stands for. It's the arm length, the effective arm length of the interferometer, 600 meters. That's why it's called GEO 600. So that's in Germany, actually not far from here. It's near Hanover. So these are gravitational wave detectors which are in operation now since a couple of years, but until now they haven't found a gravitational wave. They're extremely sensitive. So if I say they haven't found a gravitational wave, this doesn't mean that there are no signals. The problem is that there are signals all the time, yeah? But they come from something else. So the problem is to filter out the gravitational wave signals. So for instance, they can measure the tides. Yeah, Hanover is not too close to the North Sea actually, but you can easily observe the percussion coming from the tides in the measurements. Yeah? So there are little earthquakes all the time. Yeah, not the dramatic ones, fortunately, here in Germany, but there are little earthquakes all the time, and they can measure them with this apparatus with very high precision. So until now, they haven't found a gravitational wave, but we are actually eagerly awaiting these observations. There's also a gravitational wave detector of this. So these are interferometric detectors, yeah, where you use interferometry, not these resonant things I was talking about earlier. So such an interferometric gravitational wave detector is also planned to be sent up into the orbit. So this would be one with an arm length of, I think, 5,000 kilometers or something like that. This is called LISA, L-I-S-A, but it's in the planning stage, so it doesn't really exist until now. And when it will start, nobody knows for sure. So it's always pushed back into the future. Yeah, you can read start is planned for 2016, and then it's planned for 2018, and then it's pushed farther and farther. So actually, I don't know what's the present planning. So for a while, we will have to rely on these earthbound things. There are two other ones. So these were the first two which went into operation in 2002. There's also a small one in Italy, a smaller one in Italy, and another one in Japan now. But as I said, none of them has measured something until now. And the last thing on my list is 2004. We had Gravity Probe A, and probably you have already expected that then already also a Gravity Probe B will come. And actually, this did come. There was a project which was developing over, I think, almost 50 years, 45 years or something like that. It was started in the early 60s already. In 2004, it actually went up. So it was a satellite with very precise gyroscopes on board. Okay, these were little balls which acted as gyroscopes. People used to say these are the roundest balls in the universe. Yes, so they were produced with a very high precision. And what they measured was the effect of the gravitational field on the axis of these gyroscopes. And there is an effect predicted by general relativity. And it was possible to verify this effect, but actually not with the accuracy which was hoped for. Not quite with the expected accuracy, I have to say, with the expected accuracy. So some people say actually it was at least partly a failure, but I think that's too harsh. So it did measure the effect to a fairly good accuracy. Not quite that what this was expected, but it was sort of a success. So it verifies the effect of the gravitational field of the Earth, of course. So it was a satellite in Earth orbit. Effect of the gravitational field of the rotating Earth on gyroscopes. So that was another prediction from general relativity, which was verified with this experiment. So until now, general relativity can explain everything which we observe at the level of classical gravitational theory. Yeah? At the level of classical gravitational theory, general relativity can explain everything. Whenever there was an experimental test, general relativity did very well. So there was good agreement with the prediction. So you might ask, what are the open problems? Well, there are two open problems in my view. One from the experimental side. This is a direct verification of gravitational waves. We would really like to see this. We hope for this since a couple of years, but until now it has not actually happened. So the direct evidence, maybe I should push this up. Oops. Evidence for the existence of gravitational waves. So that's on the experimental side. And on the theoretical side, of course, the great challenge is the unification of general relativity and quantum theory. So general relativity is fine. General relativity and quantum theory. So I said general relativity is fine as a classical theory. But until now, it resists any attempts to unify it with quantum theory. So general relativity is a theory of the space-time, geometry, one could say. And this would require, in a certain sense, to quantize the space-time geometry. Maybe in a sense to quantize length and time intervals or things like that. But nobody knows for sure what exactly it means. Of course, there are many attempts. Many people try doing this since decades. Some people think they are on a very good way. For instance, with string theory or with loop quantum gravity. But real success, I think, has not been achieved until now. So this was outlook of what later generations will have to do. But what we do in this course here is just we will try to understand the basics of classical general relativity. And I will now enter into the formalism. And I begin this, as I said already, with a recap of special relativity. And I do this for a certain reason, because I think it's really important and certainly very helpful, and I think even important, to have a good idea of special relativity in the sense of geometric pictures, and by that I mean space-time diagrams and things like that. I think it's really important to have this at the back of your head when you begin learning general relativity. Of course, from a purely logical point of view, you could start with general relativity without ever having heard anything about special relativity. Logically, this would be possible. But I think it's not a good idea to do it in this way. So I will now recap special relativity, and in particular emphasize on space-time diagrams and this four-dimensional point of view. Yeah, so we should try to get a certain experience with thinking in 4 dimensions and calculating in 4 dimensions, even though we cannot visualize 4 dimensions. As I said already, the first worksheet will consist almost exclusively in drawings of space-time diagrams. So that's something I think we should practice then. That's enough. Oops. So the first subsection will be the special relativistic space-time. So I will recall what we mean by the space-time in the setting of special relativity. And then later, our main subject will be the general relativistic space-time. We'll then talk about what in general relativity we mean by the space-time. Now, quite generally, the space-time, usually spelled in one word. Some people spell it with a hyphen, but actually I think it's better to write it in this way. What you mean by space-time, obviously, is a combination of space and time, right? That's what the two words say. And where we think of our world around us in terms of three-dimensional space, points in space. That's something everybody has a clear understanding what is meant by that. And we also have a certain understanding of what times means. Time, a certain moment of time we can read from our clock. When we do space-time theory, so in particular relativity, then we combine the two things. And we combine them formally, in the sense that we introduce something which has 4 dimensions. Yeah, 3 spatial dimensions and a time dimension combined. And the objects which live in this space-time are events. They are something which have a here and now. Yeah? They have 3 spatial coordinates which tell you where it takes place, and they have a temporal coordinate which tells you when it takes place. So it's something, an event would, for instance, be 2 persons meet. Yeah? They both have a certain velocity, so they, they pass by each other, and the moment when they meet, that would be an event. Yeah? Or when one hand of my clock passes over the 12, that would be an event. It's always something which has a here and a now. So let me write this down. The space-time well, it's now common, as I said, just to use space-time. Originally, people said space-time continuum, but that's no longer in active use, this word, or more fully the space-time continuum. Is a set of events and each event is characterized by 3 spatial and 1 temporal coordinate. So it's a 4-dimensional thing. And different space-time theories make different models for this set of all events for the space-time. So special relativity is a certain space-time theory. It makes a special model for space-time. And general relativity is a more general theory. It makes a more general class of models for space-time. So at the moment, we just speak about special relativity. So the special relativistic space-time so it's about the mathematical structure which lives on this 4-dimensional object, right? That's what distinguishes different space-time theory. So the special relativistic space-time is fixed, can I write, by 2 postulates. I call them P1 and P2. P1 is what we call the, in German, the spezielles Relativitätsprinzip. So let me write the special relativity principle. Or in English, maybe you would put it the other way around, the principle of special relativity. But anyway, the special relativity principle. What does it say? Well, very roughly speaking, it says that if there's no force on a body, then it will move uniformly and rectilinearly. Yeah, it will move in a straight line and uniformly. Well, actually, the precise formulation is that you say there are reference systems in which this is the case. And these systems are called inertial systems. So actually, I would emphasize on the fact that certain reference systems exist. So I will write it in this way. I will phrase it in this way. So the principle says that there are, well, you may think in coordinates. So let me write there are coordinate systems for our space-time. And these distinguished coordinate systems are called inertial systems. Such that all force-free bodies, bodies on which no force is acting, which are just moving under the influence of their own inertia. That's why these systems are called inertial systems, such that all force-free bodies move uniformly on straight lines. That's the first part. And the second part is all inertial systems have equal rights. So there's no inertial system distinguished from the other ones. So that's the first postulate. It's a basic postulate, so we are not talking about proving it. Yeah? Proving would mean we derive it from something which is more elementary. But no, that's what we put at the top. So that's what we agree about, that we will accept it. And then we deduce all the results from this. So that's what we mean by a postulate. That's the first postulate. And the second one is a principle of the constancy of the speed of light. And this simply says the speed of light, or I should say, to be more precise, the vacuum speed of light. So of course, if you put matter into the way of the light, then it will move in a different way. But the vacuum speed of light has the same value, and this is usually denoted c. C in all inertial systems. Actually, P1 also holds in Newtonian mechanics. So P1 is, when Einstein introduced his theory, P1 was nothing new actually, but P2 was. P2 is really hard stuff. Yeah, if you see it for the first time, maybe you don't realize what a audacious idea this is. Usually we think of light in two ways. I think everybody uses either the idea that light is a wave or the idea that light is something like a stream of bullets, photons, particles, as you like to call it. But neither of these ideas would be compatible with P2 in an easily understandable way. If you think of light in terms of a wave, you would assume that there is a medium for this wave, like it is for sound waves. And then the state of motion of the medium would, of course, be very distinguished from other states of motion. Yeah, so the speed of light could maybe take this value c in the medium, in the system where the medium is at rest. But if you now go to another inertial system, which moves with respect to this with a certain speed, you would expect to get other speeds, right? So that's really not understandable in an easy way if you think of light in terms of a wave. You would have to think of a wave which has no medium, which is not propagating in a medium. So it would be a wave quite different from sound waves, for instance. Of course, light is a wave phenomenon, but it's not a wave which propagates in a medium. That's the first thing which we can read from this postulate. And the second thing is, if you think in terms of bullets, photons or things like that, then you would expect that the state of motion of the light source would play a role. Yeah, if you emit these bullets from a light source which is at rest here, they would move in a certain way. If you then compare this with another stream of light particles which is emitted from a moving source, a source which moves in this direction, you would assume that the speed of light would be different in this direction from this direction, right? So you would assume that the speed would be added to the speed of the source, yeah, with a correct sign. But the postulate says it's completely unaffected. So it's independent of how the source moves. You always have this speed c. So also on this particle idea, on the basis of this particle idea, it's very hard to understand this principle. So what we could do is let's just accept it and let's see what will come out of it. And well, if it is in agreement with all experiments, and actually it is, then, and all the other ideas which you could have about light are not in agreement with the experiments. Yeah? So that's a good argument to accept this postulate, even if it is not in obvious agreement with our elementary understanding. So let's accept this now and let's see what comes out of it. So these are the two postulates on which special relativity is based. Of course, I mentioned already that the most important experiment to which this has been applied is the Michelson-Morley experiment. Yeah? If this is true, if this postulate is true, then of course it's clear that the Michelson-Morley experiment must give a null result. So we can now start drawing space-time diagrams in order to visualize this space-time model a little bit. So when we do special relativity, we usually use inertial systems. You could introduce accelerated coordinates, coordinates which move with respect to an inertial system in an accelerated way. For some application, it might even be useful, but for most basic applications, we just work with inertial systems. So the first thing I will do is I will introduce names for the coordinates in an inertial system, and then we will use these for our discussion of the consequences of these two postulates. So there must be 4 coordinates, right? Space-time is a 4-dimensional thing. So notation for coordinates in an inertial system well, my convention is that I write the temporal coordinate first. The temporal coordinate would be something like t. And as the other coordinates have the dimension of a length, I make a length out of this also by multiplying it with c. C is this constant, which has a dimension of a velocity. So if you multiply a velocity with a time, you get a length, right? This is length over time. So the two times cancel each other. So this is a length. And this time coordinate I denote by x naught. And then I have the 3 spatial coordinates, usual Cartesian coordinates in my frame. And I denote them by x1, x2, and x3. And you could identify this with x, y, z, if that is your favorite notation for Cartesian coordinates. So that would be my 4 coordinates. Well, if you look in books, you will find that many authors set c equal to 1. They use units where this is not there because they set c equal to 1. So they use the same unit for length and for time. Of course, this is meaningful only if you accept these postulates. Yeah? If c would not have this fundamental character, then it would be absolutely idiotic to set c equal to 1. Yeah? It would be of the same sort by, I don't know, setting the gravitational field here on Earth, the g, which is 9 meters per second square or something like that, set this equal to 1. Yeah, this would make a mess out of all formulas which are involved with gravitational fields. So this is a good idea, possible way of doing things only if you accept this postulate, that the C really has a universal character. But then you can do it, and actually when I do calculations for myself, I always set C equal to 1. But I think I'm not allowed to do this by law in a lecture like this here. So we have to use this SI units where the C is not equal to 1, but rather 300,000 kilometers per second roughly. So you will often see this without the C. You will also often see it in the 4th place. So instead of x naught, x1, x2, x3, some people write x1, x2, x3, x4. Yeah, then it comes at the end. It's just a convention. And in old books, you will also sometimes see an I here, which is the imaginary unit. This makes some formulas simpler, but actually it destroys the whole structure of the theory. In particular, if you go to general relativity, you will see that this is really, it leads to big confusions. So this is actually no longer done. It's done in some old books, but not nowadays. So in some old books, you will find an I here. It makes some formulas simpler. This was just the reason, because sometimes this thing comes multiplied with itself, and then I squared would make a change of the sign, which is quite convenient. But you should not do this. So these are the possible other conventions you can find in books. Okay, and now let's draw space-time diagrams. We have something like 6 or 8 minutes. So this will, I think, be enough time for drawing 2 or 3 diagrams. So when we want to depict something in an inertial system, then obviously I would use these coordinates. So the usual convention is to write the x naught as a coordinates from the top to the bottom. And then you would need 3 additional dimensions in order to use the other 3 coordinates. I cannot draw a 4-dimensional picture, so I have to drop one of the 3 other coordinates. So I can have x1 here and x2 here, but the x3 you have to have in your mind. Yeah? There's no place to put it here. But you should always keep in mind that it is actually there. And now we can draw some diagrams. And the first thing I would like to draw is, where should I write this? I should have left a little bit more space here. So let me do it this way. The first thing I want to draw is a world line that's a path in space-time. Yeah, what I've drawn here is space-time. This is time and this is space. So, and a path in this space-time, that's what we call a world line. In order to distinguish it from a line or a trajectory just in space. And I want to draw the world line of a force-free body. Now, a force-free body in an inertial system is in rectilinear uniform motion. And this means its world line must be a straight line, right? Not just the projection into space is a straight line. This means that it is rectilinear in space. But this doesn't say that it is uniform. So the velocity could change in an arbitrary way. It could start very slowly, then become faster, and then again become slowly. It would still be a line in space. But it should also be uniform, so it must be a line in space-time. So let me draw it this way. It must be a straight line in space-time. So that's the world line P. Oops, world line P. So you could project it into space. So here's a vertical. Where it intersects here, you get the projection into space. And that's what we call the trajectory in space. And this angle here, this angle with a vertical, this has a geometrical meaning, or a physical meaning, I should say. So I have here this length, let me call this delta S, and let me call this length here, this coordinate length, just measured on the coordinate lines. Let me call this delta x naught. Then obviously, alpha is given by the equation that the tangent of alpha is delta S divided by delta x naught, right? But what is delta S? Delta S is a length element on this projection onto space. It's a horizontal part. So it is, if I write it out in x1, x2, x3, it's the square root of delta x1 squared plus delta x2 squared plus delta x3 squared by the Pythagorean theorem. And delta x naught is c times delta t, because x naught is c times t. And now you see this is just the velocity. This is the length increment divided by the time increment. That's the velocity, or the speed rather, the magnitude of the velocity divided by c. Oops. So this angle tells you the velocity. If v is 0, this means the object is at rest in your reference frame, then this angle would be 0. So the line would be vertical. A vertical world line is a world line of an object that is at rest in your inertial system. And the bigger alpha, the bigger the speed. And now there's an important case where this alpha becomes 45 degrees. Let's do this. Can I draw this here somewhere? Yeah, I think I can draw this here. This happens for a light signal. So I first claim it, then I explain it. World line of a light signal. So a light signal is something that moves with the speed c, right? So was a c defined. So, and if the light signal is not deviated by mirrors or things like that, then it would also move in a straight line. So a light signal is something which moves in a straight line with the speed of light. And so the world line would also be a straight line, but with a certain inclination, with a special inclination. So here I have x1, here I have x2, here I have x naught. And my claim is that this angle must be 45 degrees. So this angle here, so that's the world line Well, P stands for particle. Let me call this world line L. L stands for light. So in this case, the angle should be 45 degrees. And why is that? Because, again, we can consider here delta S and here delta x naught. So that's the angle alpha. So for light, we have, so quite generally, the tangent of alpha was v over c. But for light, the v is c. Light is something which moves with the speed. So I should maybe I should put an index here. So the v for light. The v for light is, of course, c. So this is c over c. So this is 1, and this means alpha must be 45 degrees. So a straight line which has an inclination of 45 degrees, that's a light signal. Yeah? If this angle is smaller than 45 degrees, then it is an object which moves with subluminal speed. If it is bigger than 45 degrees, it moves faster than a light signal. If something like this is possible, and for what sort of things it is possible, we will discuss very soon. So that's the first little exercise in drawing word line diagrams. And maybe you allow me to draw one more word line. This will be the last thing for today. Maybe I do this here. Yeah. The third thing I would like to do is I want to ask myself, and I want to ask you, what is the word line of an accelerated object? By what is an accelerated object distinguished from a non-accelerated, from a source-free object? Well, obviously, it is not moving uniformly in a straight line. So it could be moving in a straight line in space, but not in space-time. So the word line of an accelerated object accelerated body, I write. Yeah, something which is not a straight line. Anything which is not a straight line is accelerated. So it could be something like that. That would be an accelerated object. Yeah, it need not be in a plane. Yeah, it could be like a spiral or things like that. And it says something like a momentary speed. Yeah, at each event. So this is the word line P. At each event, you can construct this angle alpha. That's a little bit small, is it not? Let me do it a bit bigger. So this alpha gives you the speed at this event. This alpha gives you the speed at this event. And you see this will change. Yeah? The force-free objects are characterized by the fact that the alpha is constant. It's a straight line. It has always the same angle with respect to the vertical. For an accelerated body, we get different alphas for different points. So everything which is not a straight line is an accelerated body. Okay, I think I stop here, and we practice this a little bit on Wednesdays, and we will draw a lot of space-time diagrams. And I hope we will get a certain familiarity with these things, with these four-dimensional pictures, before we then move on to more challenging things. Okay, have a nice weekend.